Hello. Hi. Thank you, Xro, for the introduction. Gesundheit. Okay. Today I want to talk about this talk, from silicon to Darude Sand-storm, breaking famous synthesizer DSP. Get it? Because sand chips, silicon is made of sand. So, I'm part of this group now called the usual suspects. And what we do is that we take all synthesizers from the 90s and 2000, and we make plugins for them. We make very accurate, low-level emulation that allow you to play those synthesizers again in your DAW of choice in the most user-friendly way possible. What kind of synthesizers are talking about? We're talking about digital virtual analog. Think about, for example, the Nord Lead 2, the Access Virus, or the Waldorf stuff. Those were digital, those were based on mathematics, on algorithms. And this means that even when in some years they will all break apart, they will all cost 20,000 euros to buy, we will still able to play them again because the software that is run inside of them has been made possible to run again on modern hardware. The same way that we can play old video games with console emulators, the same thing we can do with those. We were able to emulate those models that I showed before because they are based on a DSP chip, which is a special processor, which is especially optimized to run very fast math, very fast multiplications, and those work really well for audio processing. And this is a chip made by Motorola called the DSP56K, and it was used in a lot of those devices, which is really cool because this chip is entirely documented, and so you can look through the documentation and figure out exactly how this chip works. It's like building a console emulator just by having the documentation of how the console works. You can just go through it and implement an emulator that just runs those programs. And in fact, we made it open source. If you go on GitHub right now, we have this project called the Gear Emulator, which it's a JIT-optimized 56K emulator, which runs really fast, and it's able to convert the code for those old synthesizers into ARM and x86 so that you can run it very quickly on your computers today. Eventually, though, we started looking into this boy here, the Roland JP-8000. It's a virtual analog synthesizer from 1996. And virtual analog, as in it generates sounds by using math, algorithms, and software. And it became extremely popular for certain kinds of trance music. And it was used in a lot of famous hits that probably some people here heard about. And while we made the emulation for the other models, a lot of people were still asking, can you make the JP-8000? Is it possible to emulate it? And the answer was no for a while, but then something changed. And the reason why I called the talk this way is because if you turn on the JP-8080, the first preset that appears on the keyboard is called Sand-storm, which some cool dude saw and decided to turn that into a song. So that's the relevance that this thing has in the music history. And it was also famous because it has a special kind of sound, a special kind of oscillator called SuperSaw, which is a famous kind of layer than the tune saw wave, which produces a very characteristic sound. You probably heard something about this before. What you're hearing is one of the pinnacles of trance music, which is this very thick kind of sound made with several saw waves, which was very typical of this instrument, and a lot of people tried to recreate it, maybe not so well. And it was so popular and so mysterious that people started asking, how did this work? And there were lengthy discussions in forum that started even in 2009. Some people say that it was a phase desync, which uses a carrier waves oscillator modulating its signal through a COM filter. Some other people speculated that it's actually one single oscillator that runs through a chorus and outputs phase shifted 7 times. This is currently the most realistic hypothesis. Someone said actually it's a sound coming from another planet that an alien brought that down to us. And someone went very deep studying this thing. In 2010, a guy called Adam Szabo wrote their bachelor thesis on this. And what they did is that essentially they recorded a bunch of waves from this synthesizer, and they went on with math and trying to just understand from those waves how the thing worked. What we realized, though, is that this thing is running software. And digital audio isn't magic pixie dust. It's mathematics. It's software. And if you get the math and the software right, then you can just emulate the thing and figure out how it works. So that's where we started. That's the main board of the thing, the synthesizer. And you can see that we have different parts that needs to be emulated. The first one is the microcontroller, which just controls the main part of the keyboard. And it's running H8 microcontroller with some flash memory, some RAM. And then the red squares that you see there, those are DSPs. And those execute the actual signal processing. And there are 4 of them connected in series that pass the result to the next one. And then the final DSP produces the audio output by using a digital analog converter. And the microcontroller was fairly easy, actually. It was well documented. It's an Hitachi H8S. And this handles the front panel controls and the keyboard. And it has the role of uploading the programs to the DSP. So this is a very important part to emulate, because it's essentially like emulating the CPU of a PlayStation that then communicates with the graphics card if you want to figure out the graphics card. And in fact, we finished this quite early. This was basically ready in 2023. And we built a user interface using SDL and Unity so that we could run the original firmware and see what it was doing, seeing what it printed to the LCD, see what it was uploading to the DSPs, and also tweak all the parameters to see what they did. The big problem, though, was the DSP chip. Because it's completely proprietary, there was no documentation about it, and it was only seen in Roland products. And we know that this is a programmable DSP. This is execute code. But we have no idea what this code is. Because if you look at this, it's a bunch of random bytes. Like, we run the CPU, and the CPU uploaded this thing. But then we don't know what to do with it, because this is a program for which we have no information regarding the bytecode, the encoding, how the stuff is encoded, how the program is being run. So because of this, some people already started giving up. Someone on forums was saying that, yeah, it's probably impossible. We just have to enjoy the hardware until it lasts and then just give up. And if we don't have a datasheet, then we'll never make it. We didn't accept his answer, because there must be a way. So what did we do? We started decapping the chips, which is a very common thing to do in our arcade and console emulation. And this is actually not the first time that I'm doing it. I have to say, I have no idea how this works. I'm a software engineer, and I know, unfortunately, very little about hardware. But still, I somehow managed last year at Congress to present a talk about this. I reverse engineered a piano module from Roland from 1986. But by essentially tracing all the wires, all the blue decoration that you see there, those are all the wires present in the chip. And by figuring out what each cell did, and then by running a simulation using Verilog. The problem is that this is a chip from 1986. And we're talking about something that it was released in 1996. We have 10 years apart. And we know that back then, technology advanced really fast. Which was a problem, because in fact, this was the chip that we had to deal with. This was a lot more complicated. But we can still figure out some things. Those very repeated areas that you see there, this is static RAM. which is a few kilobytes of RAM that probably keeps some variables or the program or stuff like that. And the trench in the middle that you see, it's called standard cell logic. We can zoom in. Which, if you see, it's a series of rows which implement some logic gates. Think about AND, OR, XOR, and so on. And each one of them, it's connected through wires that are both horizontal and vertical. You can see like 2 layers of wires, one that it's on the top layer that is more blue, and another one that is more orange. And you can see all of those rows in which all the cell circuit is present. And those effectively implement a digital circuit. If you probably saw this in engineering or computer science, this is an example of, like, for example, an adder, in which by using a sequence of AND and OR and NOT gates and XOR gates, you can implement mathematics and logic. And this is all stuff that you can emulate in software. But first, you need to figure out how the chip works. We had, for example, to identify all the logic cells that we found. The idea is that each cell implements a certain logic function. And what we found is that the vias, which are those dots that you see in the chip, in the cell, those are kind of consistent. So if we manage to train a machine learning model to recognize those vias, then we can use some matching using convolution to directly find all the instances of the cell. And the video that I'm showing here, it's essentially every instance of that chip, of that cell in the chip, recognized basically using machine learning, and every time that it appeared. And you can see that the wiring on top of it changes, but essentially it's the same cell. And we didn't do this alone. We had help from this very cool guy that you can follow him around the social media, and he takes amazing pictures of semiconductors, and he's the one that figured out all these things about how to reverse engineer the silicon. And this is an example, for example, of a XOR gate. And here you can see a very cool animation of this cell and all the metal bits that turn on and off when you apply current. Obviously, the chip doesn't light up like this, but it's a representation to show you where the current is going, so you can figure out from a tiny picture of a circuit which kind of logic function is implementing. And eventually, using those matching and machine learning techniques, we figure out all the cells. This is a map that shows you on the chip where each cell is and what kind of cell it is, color-coded. For example, the orange and the green ones, those are AND and other logic cells. And so this is cool, because this way we automated a lot of the work. The problem, though, is that how are those cells connected? We have to also figure out the wires. And the idea is that there are 2 layers of wiring on top of each other, like in a PCB. The top layer was actually kind of easy, because if you use some special microscope lenses, you can focus on the first topmost layer of the silicon and have everything else underneath be blurred, which, with this, you can do something cool and essentially use computer vision techniques to just extract those pixels and remove all the blurred ones. And by merging this data with the cells that we found before, we can essentially connect all the dots and figure out the top metal entirely, which is really cool. Another part of the process that we automated. When we wanted to extract the bottom connections, though, we hit a giant roadblock. The way that you normally do this, it's by doing lapping, which basically means taking your chip and sending it down micrometer by micrometer until you remove enough material. The problem is that every time you do that, it's extremely time-consuming, it's extremely unreliable, produces noisy results, and if your chip is not perfectly aligned, you will basically remove more material on one side than the other, so it's a bit of a nightmare. And the solution here was to do manual tracing, which means going back to that picture that I showed of the chip before and clicking and drawing all the wires manually, which you can imagine how much time that would have taken, which is realistically like 1 month of work, which I don't want to do that. And so at that point, the work kind of slowed down. Until a new player arrived in town, Arturia, which is another big company that releases plugins, released their emulation of the JP-8000. The problem is that it's not really an emulation. It's more like some code that they put together that sounds similar to it, but you can clearly hear that there are a lot of differences, and this is because it's not running the original software. So at this point, we were like, yeah, we'd have to do it better. Can we learn anything by pausing the silicon work and probing the hardware instead? Like, we learned a lot from the hardware already. We know generally what it's supposed to do. Can we figure out anything else just by probing the hardware? And yeah, the plan B is poke it with a stick and see what happens. You don't destroy the chip. You treat it as a black box. And if those DSP execute programs, this means that you can send programs to them and see what they do. It's like, imagine figuring out an architecture that you never used before. You can try to send programs to it and see what it does. Maybe it returns some output. Maybe you learn something from it. And again, this is not the first time that I'm doing this. I did this a few months ago at Gulasch Programmiernacht. And I reverse engineered something way more simple that was a cheap guitar pedal board from the 90s. And I essentially applied this method, run programs on it, and see what happens. So this is the test interface, test setup that we built. We used a board with a chip and an Arduino Mega, which has a lot of pins, works at 5 volts, great. And we connected the host interface of the chip to the Arduino. And thankfully, we didn't need to destroy another synthesizer, since they are pretty expensive already, because we found that that chip was used in a lot of stuff, even like this expansion bar that is wildly available on eBay right now. But still, we have a bunch of questions. How does this interface between the CPU and the DSP works? How do we upload programs? How do we start and stop the programs? How do we read the results? So we started with a bit of an easier target. This thing here, it's effect racked unit, which coincidentally used basically the same architecture, same DSP, just 1 instead of 4, same CPU, and it has a very interesting test mode. If you look here, this is the service manual. It states that there are a specific combination of keys that if you press them, it will test the DSP chip. And it will return very nice error messages if we got something wrong. And this suggested the existence of a bunch of memory areas, like PR0, program 0 maybe, program 1, ERAM, GRAM. Maybe we can just run those test modes and see what they do. And maybe this way figure out how to upload a program. And with this, in fact, we figured out a bunch of things, like the fact that there are 2 program memories, each one 768 words, so 768 instructions. Maybe it's dual core. Spoiler, it is. The instructions are 24 and 28-bit respectively, which very nice match with what we saw on the silicon. And there is an internal RAM, which is not accessible. GRAM, which we still don't know what the G stands for, probably the great RAM, or I don't know. And then we started using the effect unit emulator to figure out some things of the bytecode. If you think about it, when you change the volume, you turn the volume up and down, that must be a multiplication, because that's how volume is applied in DSP. So we observed that by changing the volume, you can see how there were some coefficients in the program that changed. And with that, we figured out, the last 8 bits of each instruction, that's a coefficient. That's a signed integer. And with this, we started figuring out some parts of the instruction format. Then we figured out more things. We figured out that by changing the delay time, other parts of the program changed. Changing the delay time essentially means changing some parameters in how you read the RAM. So with that, we figured out that there was a specific pattern that was used to encode those parameters as well. So we figured out more bits of the opcode. And then to figure out even more how the RAM worked, we exploited the fact that we know how the RAM works because it's DRAM. The DRAM always use the cast, the RAS, the fast page mode, all those things that are common to all DRAM chips. So we can just solder a bunch of wires to it, attach a logic analyzer, and see what it's doing. So we basically spam random RAM commands until we saw that, this means read, this means write at this address. And eventually we figured out those commands as well. We also found some very cool opcodes. For example, this thing here turned out to send a result back to the CPU. Which you see where I'm going with this? Imagine having a program that you can run whatever you want and then read what's the result. This means that we can get data back. We can start testing the instructions. And that's exactly what we did. We put a random instruction there, send it back to the Arduino, read what the Arduino is saying, maybe you figure out something. We figure out, for example, that that's the command to load an immediate, that whatever you put there, it was just being mirrored out in the output. And we repeated this more and more until we figured out multiplication, subtraction, control flow. Some control flow things were really weird. So we essentially spent a lot of time on this, just probing the hardware and see what it's doing. And eventually, with combining all this information and what we found on the silicon, we got, well, basically we reconstructed the datasheet of the chip, which, yeah, it has 2 cores, multiplier, 24 bits, 2 accumulators. The program can be 766 instructions. There is some internal RAM, 24 bits each. Only 1 core can access the external RAM. And there is also some shared RAM, because essentially you have those 2 cores with its own memory, and then a third global memory, GRAM, which is used to communicate between each other. And if we look at the instructions that we found, the chip is extremely simple. Each instruction performs something like, it's called a MAC, multiply and accumulate, which is super typical for DSP stuff. Each instruction does accumulator plus equals some value in RAM per a constant. And if you have this kind of instruction, you can implement a lot of DSP stuff. You can implement an oscillator, a filter, an equalizer, chorusing. And it has also some other opcodes to implement these. For example, store the result to RAM, store the result unsaturated, which is used for module operations, read and write the GRAM for communicating with the other cores, and multiplication per variable, and rectify, clamp, interpolate, which are fancy names to call the absolute value, essentially. And it also has some very weird control flow inside. There are some special registers that if you write to them, you can perform a jump on always 0, positive and negative. And it has a very funky instruction which allows performing a skip based on condition. It's essentially an instruction that skips the following instructions if certain conditions are met. Which turns out it's extremely similar to the LSP, the one that I talked about in GPN. They're the same instruction format, the same memory addressing, the same external memory control, same coefficient size. We figured out that that cheap pedal board for the guitar from the 90s essentially had almost the same instruction set as the expensive synthesizer from a few years later, which they just pretty much added another core, made it run faster. But this proves how reverse engineering is very much knowing what's already around so that you can figure out the next thing easier. It's a long process. We had to make sure that the quality was high, though, because the chip is very complicated. So we essentially implemented a bunch of unit tests. And it was cool because with the unit tests, we were able to check them also against the hardware. So we have a bunch of unit tests that you can connect the Arduino to your computer, and they either check specific cases, or we also do fuzzing, which means spamming random instructions and checking that the emulator and the real hardware works exactly the same way. We also compare the audio out, because that way we can actually match that the beats that the emulator produces are exactly the same that the original hardware makes. Because if you don't get everything right, some things get really weird. That below was supposed to be a sine wave. That's a very spicy sine wave. And do you like DC offset? Well, us too. Look at that wave where it's going. That's clearly a bug. And even though, admittedly, the one below, we figured out it was a problem with memory management in C++, but that's another thing. So we built basically a nice C++ class to emulate the DSP. And one night I was like, yeah, let's do it. I connected it to the emulator for the JP-8000, the keyboard. And we run only the first DSP. We excluded all the others, and we just got the output from the first one, because, as I said before, they're connected in series. And we rendered some audio, put in Audacity, and that's what we got. That's a SuperSaw. So the magical thing that everybody was looking for, we got it. And then what was left? Putting everything together. We instantiate the class for the DSP 4 times, because there are 4 DSP. We make them communicate. We figured out how they pass variables to each other, and then get the output from the last one. So we try to play the demo songs, and this is what came out. Which are the demo songs? They were working, but they were slower than real time. It's producing audio slower than it's supposed to. So our emulator worked, but it was extremely slow. Like, this is how it was supposed to sound, but there are tiny silences in between. So, back to the drawing board. We started optimizing. We basically pre-decoded the instructions so that we don't have to perform bitwise operations thousands of times per second. Sorry, millions of times per second, but we can just pre-compute everything. We flatten a bunch of instructions. We remove all the instructions which are like knobs. And we flatten the accumulators. We remove the pipeline so that we end up with something that is very compact and way easier to execute. But it was still not enough. We had to do JIT, which essentially means converting the DSP bytecode to x86 or ARM. And we use a very cool library called the ASM-JIT, which essentially allows us to get the DSP program, perform a for loop, and for each instruction, just output what would be the equivalent in ARM or x86. This turned out to be really, really fast. Like, we went from slower than real time to 5 times real time, at least on my MacBook. And that was great, because it means that on a single core, you are expected to be able to run 5 plugins at the same time, which is really nice. Thank you. So the last question is, how does the SuperSaw work? Because everybody was making those wild theories, and we have the emulator now. We're just emulating the thing. We still haven't looked inside the code. Well, we kind of did. While during the development of the emulator, we had to build a bunch of development tools. One of those was a disassembler, which essentially gets the bytecode that is uploaded to DSP and just outputs some symbolic code. And one of our guys was going on vacation, and he was like, hell with it. I'm printing everything, because I'm not bringing my laptop. And he stayed there one night converting everything to C. And then he posted the results on our Discord channel, and we were like, wait, that's it? So how does it work? It's 7 naive saw waves passed through an high-pass filter, which means that it's 7 counters, basically things that just count plus something every time. And just they are high-passed at the end. And one thing that is maybe a bit tricky, it's the table of coefficients, which are like the coefficient to detune the oscillators, which were done with integer math, so they're a bit hard to get right. There is no modulation, no phase trick, no chorus. And how did they make this sound good? Because this will alias. If everybody knows anything about audio, you can't just do a saw wave oscillator like this. Well, back then they were like, yeah, let's just run it double the sample rate. So the entire thing is running at 88.2 kilohertz, and then they're just outputting higher sample rate. And this does the job. Because normally you will need to do a lot of math to remove the aliasing, but this is not doing it. And how close did the guy that wrote his paper about it get to it? One thing that he tried to figure out were the coefficients for the tuning. And he did it by just doing math on the audio, and we had the actual program. And if you see, it got really close. Like we got 0.11 versus 0.109, 0.006 versus 0.062. So he got really close with this. So props to him. But let's get back to this. What we did is that we also did a plugin. This is the interface that we developed for it, which closely models the original, so that you can have a very similar experience to what you had originally. And we posted this as a closed beta, and people apparently liked it. So far that Darude, the guy from Sand-storm, started posting it on Instagram. And not only, there were some people under a YouTube video that said, well, mine sounds different. Actually, it doesn't have the original thing. Darude started arguing with them. So thanks, Darude, for defending us. And this is the demo that we posted. All the sounds that you're hearing are all coming from the synthesizer that we made. Sorry, that we emulated. Don't want to get in trouble with it. So, you heard this. Maybe some of you will be asking, well, can I try it? Yeah, it's in closed beta right now. So when will the plugin be available? Hopefully now. I think that right now we posted the code on GitHub. So the code is there. It's probably a mess, but it works. And we released it, so you can download it and try it. Thank you.
Well-deserved applause.
Thank you, thank you.
Great release, so awesome. So we have about 5 minutes for Q&A, so if you have questions, please queue up on the microphones. If you're in the stream, please use Matrix or IRC to post your channel, and our nice Signal Angel will take your questions. And does the Signal Angel already have a question? Yes.
Yeah, the internet wants to know, sand it down. Why didn't you just etch it away or laser it away?
Who? Can you repeat the question, sorry?
The question was about why you sanded down the chip and not etched it away or use lasers.
Oh, because if you sand down the chip, then you can remove the two layers of metal separately. If you just use hydrofluoric acid, you're basically going to remove everything down to the poly layer, which kind of makes it useful if you're interested into the poly, but not really interested if you want to look at the second layer of metal. But again, I have no idea what I'm talking about. The main reason is that the guy that we work with doesn't really want to work with hydrofluoric acid, and neither do I. And those things are really expensive, and we are running on basically money that we put ourselves and donations to make this work.
Okay. Question from microphone number 2, please.
Yep. Really appreciate you doing all this work and the entire community that helped out. When you hit the performance issues in your first version of this implementation, were there other techniques that you investigated for speed up? Potentially even going to an FPGA or doing something more parallel?
Yeah. I mean, you can go with an FPGA. The problem is that then you're basically re-implementing the entire chip, which means that you have to make a PCB for it, which means that it doesn't run on your laptop anymore. And parallelizing the thing, yes. The problem is that those 4 DSPs are basically running the program separately and then every time passing the data to each other, which means that if you want to parallelize the 4 DSPs, then it means that every thread is waiting on each other. So we tried doing that. The problem is that it's really not efficient because it's more the communication hover between the threads than everything else. And also, if you want to just parallelize on the samples, you cannot really predict the future, so that means that you introduce a lot of delay. So that wasn't really an option. The only option here was to do a JIT, unfortunately.
Cool. Thanks again.
Nice. Microphone number 1, please.
Yeah, how would Sabo's method perform compared to yours?
Well, the work that Sabo did is actually very, very cool. He just, I think, released a plugin entirely based on it, entirely based on looking at the audio from outside, which produced also a result that was very, 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 very close to the original. The problem is that we wanted to do a low-level emulation because we wanted to run the original. It's like the equivalent between running the original game in an emulator of the console or re-implementing the game from scratch just by looking at it, which both approaches are great. Both plugins, I think, they work really well, but they're fundamentally 2 different approaches to the thing.
Microphone number 2, please.
Yeah, thanks a lot to you and your team for this amazing work. I will try it out later, I would say. And did you earn any insights from grinding up that chip that helped you later in development of the plugin, or did this work go to waste?
No, it didn't go to waste because there were a bunch of things in which we were trying to figure out, for example, how an interrupt line worked. And we couldn't figure it out, but what we did is that we did manual tracing just precisely for that interrupt line, and eventually we figured out how well it connected, and that way we were able to figure out quickly how that thing worked, because otherwise we'll never figure it out. Another cool thing is that if you look at this picture here, here, you can see how you have clearly 2 areas that are like orange and green, 1 cluster up there and 1 cluster there. And what essentially that circuits implement, it's a multiplier. A circuit that you give it an 8-bit and 24-bit number, and just in 1 clock cycle perform multiplication, which means that you have to have a lot of AND and others logic gates. And with that we figured out, oh, there are 2 spots there. Could it be that there are 2 multipliers? Could it be that that means that it's dual core? And that was the thing that which we figured out it was dual core, essentially.
Thank you.
So I've been told we're out of time for today. So one more big applause, please, for Giulio.
Thank you.